So next section we're going to look at is the fundamental theorem of algebra, which I always like saying. Sounds really impressive. So we'll have a look at the definition of it and then a couple of examples as well. So to define the fundamental theorem of algebra, you probably already know this, but if p of x is a polynomial, degree n, x to the power of 5 is the highest factor, so it will be a degree 5. For example, so if p of x is a polynomial of degree n, then p of x has exactly n zeros, each of which may be written in the form of a plus bi, where a and b belong to the set of real numbers. Some of these can be repeated as well. Okay, so that's the fundamental theorem of algebra. All right, so using the fundamental theorem of algebra, the following properties can be established. So every real polynomial, emphasis on real, can be of degree n, can be factorized into n complex linear factors. Okay, some of which may be repeated. We can always get it down to a linear term, so x minus something. Every real polynomial can be expressed as a product of real linear and real irreducible quadratic factors. All right, so this little delta has to be greater than 0. It has to be less than 0. Delta has to be less than 0, and that delta is what we call, if you remember, the discriminant. If I just jump across here, that was when we had a quadratic equation. As you can see highlighted in orange, b squared take 4ac, that's the discriminant. So if you look at that and that's less than 0, then that second rule applies. All right. Next one, every real polynomial of degree n has exactly n zeros, some of which may be repeated. So again, that was in the definition. If p plus qi, where q is not 0, is a 0 of a real polynomial, then its complex conjugate, so we just change that sign in front of I, that's what a conjugate means, complex conjugate, is also a 0. And finally, every real polynomial of odd degree has at least one real 0, okay, because they have to be pairs. If we have an odd degree, one of them has to be 0. All right, so that's just a bit of a definition. Let's go into a couple of examples. All right, so suppose minus 3 plus I is a 0 of p of x, and p of x equals ax cubed plus 9x squared plus ax minus 30, where a is real. Find a, and hence find all the zeros of the cubic. All right, so because this is real, the polynomial, which said somewhere, real, yep. We know that if minus 3 plus I is a 0, then minus 3 minus I, its complex conjugate, is also a 0. So we've got two of the zeros, and what we can do is make them into a quadratic. So if I find the sum, so the sum of these two, it's minus 3 plus I plus minus 3, take I. The i's cancel out, and I'm left with minus 6. All right, and the product is these things multiplied by themselves, so minus 3 plus I times by minus 3 subtract I. If we expand using FOIL, it's going to be negative 3 squared, which is 9, plus 3i minus 3i minus I squared, okay, which equals 9. These two cancel out in the middle. Take negative 1, which equals 10. All right, so therefore, if I wrote these two as a quadratic, you write x squared, then you can subtract the sum, so take away, it's a negative 6, so it becomes plus 6x plus 10 for the product. All right, so that's going to be one of the quadratic factors. All right, so therefore we know that our original, so ax cubed plus 9x squared plus ax minus 30 has to equal this thing here, x squared plus 6x plus 10, times by a linear factor. So let's call it, I don't know, hx plus j. All right. Now, the trick with this is we know that to get the x cubed, it has to be that x times this x. All right. We know the factor is a in front of it. So that means our h has to equal a. So we could rewrite this as x squared plus 6x plus 10 times by a plus, okay, we know that this last term has to multiply into the 10 to make negative 30. So our j has to be, so our j has to be negative 3, because that's the only way we can make negative 30 on that side. All right, so next step is to find out what this a is. If we expand this out to its maximum, we're going to get this equals ax squared, cubed, plus, if we times our x by our x, we're going to get our x squared, so 6a is going to be our first lot of x squareds, but we're also going to get this negative 3, so take 3. Both of those are going to be x squareds. Our x's are going to come from our negative 3 times 6, so let's go plus negative 18, and the other x is going to come from the a times the 10, plus 10ax, and finally we're going to get minus 30. All right, so now if we have a look at both sides, so we have a look at, because these things are equal to each other, we can do a bit of a calculation and try and work out what this a equals. So equating coefficients of x squared. So on the left-hand side, we've got 9, and that's going to equal, on this side, we've got 6a minus 3. All right, we do a bit of shuffling. I might run out of room here, but we get 12 equals 6a, therefore a equals 2. All right, you could also try that with the x, and it would come out to be the same thing. But yeah, we've found that a. Okay, so what we've got here is we found our a equals 2, therefore the combination of this quadratic is x squared plus 6x plus 10, and then 2x minus 3. All right, we have been asked, so it's always good to go back to the questions, find a and hence find all the zeros. So we don't know the zeros of this side, so if 2x minus 3 equals 0, we would get 2x equals 3, x equals 3 divided by 2. All right, so therefore, zeros are, we know it was negative 3 plus or minus I, and also 3 over 2. All right, so that's we've been able to find the zeros and answer the question. So, yep, good. Let's move on to the next one. So I think this is a really excellent question, and let's have a look at it. So one zero of ax cubed plus a plus 1 x squared plus 10x plus 15, where a belongs to real numbers, is purely imaginary. Find a, and the zero is the polynomial. Okay, so let's let. I'm just trying to get my pen working again. So let's let the purely imaginary zero be bi, where b does not equal 0. And since we were told that p of x is real, then we have bi, so we've said that the purely imaginary one is bi, and its conjugate, so negative bi, are zeros. All right, so we've got both. Now, if we take the sum, so the sum of these, so if we add them together, they're going to equal 0, because that's what conjugates do if there's no real part. And the product equals b squared, so negative b squared times by I squared, which equals, because I squared is -1, it just equals b squared. All right, so therefore the zeros of plus or minus bi come from x squared plus b squared. Okay, and we're going to be able to use this to help us work out what a is. Alrighty, so consequently, so because of this, we get the original term, so ax cubed plus a plus 1x squared plus 10x plus 15 is going to equal x squared plus b squared. All right, we know it's got to be another linear term because it's power of 3. So it's going to be ax plus 15 over b squared. Okay, now you might be saying, why did I get ax here? Why didn't I just leave it as like h and j or just some complete unknowns? Because I could see here that to make x cubed, there had to be an a in front of it. So I had to add the a here. And to make 15, I had to have 15 times b squared divided by b squared to get rid of that b squared. Okay, so again, hopefully you've got that, but if I expand it out, I get ax cubed plus 15 over b squared x squared plus ab squared x plus 15. All right, so now if I have a look at the coefficients, so both sides, so equating coefficients of x squared gives, so if I look at my x squared, what I'm going to get is a plus 1 on my left hand side is going to equal 15 over b squared. All right, and if I do the same thing, so equating coefficients, these double lines mean the same thing, but instead of x squared, I'm going to do x. I will get ab squared on the right hand side equals 10. All right, we should be able to use these to get a and b. All right, so let's call this, let's call this equation 1 and 2. All right, I need a little bit more room, so let's just call this equation 1 and 2. All right, so now if I rearrange 1, so rearranging 1, equation 1, I get a, at the moment it's a plus 1 equals 15 over b squared. But if I times both sides by b squared, I'll get ab squared plus b squared equals 15. Now the reason I've done this is because I know ab squared equals 2 is 10 in equation 2. So I can change this first ab squared into 10. So 10 plus b squared equals 15. That means b squared equals 5 and b equals the square root of 5. Now, what I can do is same thing. I can just put that b back into the other side. So let's put that b, let's put this into equation, it doesn't matter, equation 1. So a plus 1 equals 15 over, we know b squared is 5, so 15 over 5. So that means a equals 15 divided by 5 is 3, take away 1, so a equals 2. So now we've got our a and our b, and we can move from here. So therefore, our linear factor, which was ax plus 15 over b squared, we can put those in there. So now we get that equals 2x plus 15 over b squared was 5, so plus 3. All right, and again, if we set this equal to 0, we're going to get our roots, which are going to be x equals 2 over, or negative 2 over 3. Oh, sorry, negative 3 over 2. All right, therefore, our roots are -3/2, and also plus or minus our b, which was plus or minus square root of 5i. So that's a really good question. I really like that one, but hopefully we can have a go at some ourselves now. Thank you.